concentration. And so this other way that we have of measuring the concentration of a solution is called molality. And the formula is just sitting right there for you. It is the number of moles of solute divided by the number of kilograms of solvent. All right. And so what we'll do is just a quickie example or two here, just to make sure that you know how to do this. And it also might require, and I should have had a little paper copy of a periodic table handy, but I don't. So we'll just do this. So let's go ahead and figure out what the molality, and molality is little lowercase m. If I have 3 moles of solution, 3 moles of sodium chloride, and I'll come over here to you, Jack. Jack, is the NaCl, which is being dissolved into a kilogram of water, is the NaCl your solute or your solvent?
Solute.
Perfect. So I'm going to just label it as such. So that's the solute. So that means that the kilogram of water, Jack, must be the
solvent.
Yep, good stuff. Because if we accidentally mix those up, then we'll end up with problems here. So if I want to find the molality, how much moles of solute per kilograms of solvent, this one's pretty straightforward. We're going to literally just go 3 moles divided by 1 kilogram. And so we've got 3. And then the units, they're strange, but it's just lowercase m, all right? And you could also write it as 3 molal. All right, so you can do a 3 with a lowercase m or 3 molal. All right, and we'll do one other one here. And then the harder one, the one that's maybe the most important part of our lesson today, is actually the second page of this assignment. So if I wanted to find the molality, and Jack, thank you for your help with that. If I wanted to find the molality of this guy, all right, 25 grams of silver nitrate dissolved into 2 kilograms of water. Same deal here, Stella, if you could help us out here. Is the AgNO3 the solute or the solvent?
The solute.
Yep, and so I just like to label it just to keep my things straight. And the water must then be the?
Solvent.
Solvent, perfect. All right, so let's go ahead and do this calculation together real fast. So I've got now, Stella, if I'm supposed to do moles of solute, but I've given you grams, what do I have to do? Can I use 25 grams in my formula?
No, you have to convert.
Okay, so let's go back and remember how to do that. 25 grams of AgNO3. And this is where we're going to probably have to pull out our old periodic table. And honestly, I don't want us to get too far into this. I just wanted to show you the key points here. Stella, you look up the periodic table. The mass of silver, how many silvers would you have?
One.
And how many nitrogens?
One.
Yeah, and how many oxygens?
3.
Perfect. All right, so you'd add those all together, and that would be your molar mass that you'd put down here. And then up top, you would put 1 mole of AgNO3. And so whatever we get from this calculation, that number is going to go right up here at the top. Stella, what would we put in the bottom of this molality calculation if I have to put kilograms of solvent? What should I put down here?
2 kilograms of water.
Perfect. And so literally just go with 2 kilograms. Okay, so at this point, I'm going to leave the rest of this to you guys because I want to go into the second sheet. But I do want to highlight one thing. If you look at some of these problems where I give you a grams of a solute, make sure that you convert those grams into moles, and you do that properly. One thing that's tricky here is if I'm dissolving it into 500 grams of alcohol, so the solvent in this case is not water, it's alcohol. I'm going to come back to you, Jack. If it's 500 grams and I look at the formula for molality, what do I have to be careful of here, bud?
Make it into kilograms.
Yeah, and so let's just remind ourselves, how many grams are there in 1 kilogram? Do you know off the top of your head, Jack?
1,000, I'm pretty sure.
Yeah, you're exactly right. So don't forget, anytime you end up with one of those guys, right, you just want to make sure that you use the appropriate units, okay? So I'll post answers to this tomorrow so that you can work and check yourself. But the real meat of today's work is on this second page. And I'm going to zoom out just a little bit. I'll zoom in just a short bit. But there's all kinds of stuff going on here. And we introduced this a couple of days ago. And there's this idea that I can change the boiling point or the freezing point of a pure substance by dissolving in a particular solute. And the formula that we use for this, and if you recall or you weren't here or you just need a reminder, the change in temperature, and this is for a boiling point elevation or a freezing point depression. The amount by which the boiling point or freezing point changes, that's delta T, is given by this formula, imK. And we're going to talk about what those three things are as we sort of work across this table here. So here's what we're going to do. We're going to think about dissolving 5 grams of caffeine into 250 grams of water. And the first thing that this asks us to do, because this formula requires us to know 3 things to find how much the boiling point or freezing point changes. We have to know what I is, what little m and little mk are. So little m is molality, which is why we started off with the practice that we just did. So let's remind ourselves what little m is. It's the number of moles of solute divided the number of kilograms of solvent. Now, I'm going to have to do some math here, and I'm hoping, Stella, you can maybe help us out. As I look at these two things, I know which one is the solute, and I know which one is the solvent, all right? Is this what I'm going to put, 5 grams? Is that what I'm going to put in the top of this formula here? What does N stand for?
Number of moles.
Yeah, so unfortunately, is this the number of moles?
Oh, no.
No, so what I've got to do is I've got to convert 5 grams of C8, H10, N4O2. I've got to convert that into moles. Now, I do happen to remember some things. My brain hasn't completely turned to mush, right? Mass of carbon is 12, and then there's 8 of them. So I'm going to kind of do some mental math here. And if I make a mistake, please holler out here. 8 times 12. I think that that's 76. No, my brain is mush. 8 times 12. How about 96? Can one of you guys say that that's right?
Yeah, that's right.
All right. What's the mass of hydrogen? Hopefully we remember that. Is that 1?
Yeah.
So there's 10 of them. So we're going to add in 10. Nitrogen, the mass of 1 nitrogen is 14. So if I have 4 of them, let's see here, 28. I want to say that that's 56. And if you've got a calculator, you're awesome. Oxygen is 16. There's 2 of them. So that's going to be 32. Now, at this point, we're going to have to break down and do some math. So 96 and 10 is 106. 162. I want to say that that's 194. And for the good folks at home, hopefully I've done that right. That is the molar mass of C8H10N4O2. Because I'm doing all of this to try and convert from grams to moles, I should put 1 mole up top. C8H10N4O2. And I'm going to try and do this on my calculator here on the computer without messing things up too much. And if you have the capability of it, go ahead and check me. I'm doing 5 divided by 194. 5 divided by 194. And so 0.026 is what I'm getting there. So that's the number of moles that we're looking at. You guys with me so far? Hopefully,
Yeah.
hopefully no news is good news there. All right, so then we're going to divide by. I'm going to come over there to Jack. If I have 250 grams of water, water is definitely my solvent. What should I put in the bottom of my formula for molality? We may have lost you there for technical difficulties. Jack, I'll answer it for you there, and hopefully you get back to us soon. 250 grams is 0.25 kilograms. So at this point, excuse me, I'm going to go ahead and do this math, and I'm going to divide it by 0.25. And so the little m, the molality of this particular solution is 0.1. So I'm going to put a little box around that so that I know what it is. So in my formula for figuring out how much the boiling point or the freezing point has changed, we've got little m. And the second piece of this, we talked a little bit about it a couple days ago. I, the Vant Hoff factor, that's what I is. And really what you have to remember for the Vant Hoff factor is simply this. If it is an ionic compound, you want to figure out how many ions are in the compound itself, so that when you dissolve it, it breaks into however many ions. And we'll look at that in this second one in just a minute. Excuse me. Since we had issues there, Jack, for a second ago, Stella, I'm hoping you can hear me. Stella, can you tell me, is this an ionic or a molecular compound, this caffeine molecule?
I think it's an ionic.
Okay.
Actually, no, I think it's molecular.
Ionic,
I don't know.
It's okay. Ionic compounds are always metals with nonmetals. Do you see any metals in this compound?
Hydrogen is on the metal side.
It is, but remember how it pokes out up there because it's kind of different? Yeah. So even though it is on the metal side, do you really see any metals here?
No.
No. So if it's all nonmetals, ionic or molecular, ionic or covalent, which one?
Molecular.
Yep. Okay. So here's the beauty of it. As soon as you identify that it is molecular, that it is covalent, your I value is always going to be 1. So now we're basically 2/3 of the way home. And now here's the beautiful thing. All right. K is just a constant. If you imagine that we were terrible spellers and we spelled constant with a K, all right? And there's a constant for boiling of water, and there's a constant for freezing of water. So if I want to know how much has the boiling point changed, this says delta T. I know it's a little bit small. Delta T, the change in your boiling point. All I have to do is use the I value that I've calculated, the M value that I've calculated, and the K value that will usually be given to you. So what I'm going to do is I'm going to throw these 3 numbers in the calculator, because delta T is equal to imK. And if it's delta T for the boiling point, I'm going to use the constant for the boiling point. So that's going to be equal to, I was equal to 1, M was equal to 0.1, and the K for the B is 0.512. So throwing that all in our calculator, we should be just moving some decimal points here. 1 times 0.1 would be 0.1. 0.1 times 0.512. I think that that would be 0.0512. Give me some sort of sign, Jack and Stella, that you're doing okay so far.
Yeah.
Jack, you there? You're still muted there, Jack. So hopefully you're all good. All right.
What did you say?
Jack, are you still doing okay? Are we
Yeah.
with you? Okay. So at this point, I'm going to jump over this delta T here. So we know that normally water boils, all right, because we dissolve this in water. Water normally boils at 100 degrees Celsius. So the new boiling point is obviously going to be its boiling point elevation. So the boiling point has gone up by this number, 0.0512 degrees. So the new boiling point, when I dissolve 5 grams of caffeine into this amount of water, that water is actually going to boil at this number of degrees Celsius, 100.0512. And that's all we're doing with this boiling point elevation and this freezing point depression, this delta T equals imK stuff. So we're going to do the next one here, delta TF equals imK. And all we're going to do is plunk in the values. So we know that I is still equal to 1. We know that M is still equal to 0.1. But this time, because it's not the boiling point we're talking about, it's the freezing point that we're talking about, there's a, excuse me, something in my throat. There's a different K value that we use. So we plug that value in, 1.86. And so now it's 1 times 0.1 times 1.86. So if I'm doing my math in my head right, it's going to be 0.186. So at this point, we come over here and we know that water normally freezes at 0 degrees. But remember, it's freezing point depression. So when we add in this caffeine, we're making it a little harder for the water molecules to come together and to bond with each other and freeze up to go from that liquid state to the solid state. So we're lowering the freezing point by 0.186 degrees. So now the new freezing point would be negative 0.186 degrees Celsius. So here, when we were talking about the boiling point, we added our delta T number. When we're talking about freezing, we subtracted. And so that's the essence of the calculations that we want to be able to do here with this stuff. All right. So we pause for a second. Anything from you guys that you want to ask about?
No, I'm following along pretty well.
Okay, cool. So I'm not going to do the last one completely with you here because I want to go ahead and give you a little bit of time to wrestle with it on your own. But I will do this. I will look at this and say, let's write the formula for sodium sulfate. And if you don't have a periodic table in front of you, maybe you find one. Pause this if you're watching on video. Since we're doing this live here, guys, sodium is +1. Sulfate is -2. So I'm going to need 2 sodiums to match up with that 1 sulfate ion. So I'm going to do a similar calculation for molality. I'm going to have to convert this number of grams of this into moles, divide it by the kilograms of solvent. But this is the one that I wanted to emphasize, and then we're going to call it a day. Jack, if you're good here, if I take Na2SO4 and I dissolve it in water, how many sodium ions am I going to get?
2.
I'm going to get 2. How many sulfate ions am I going to get?
1.
So if I think about this particular compound dissolving in, what's the I number got to be?
3.
Yep. Because it's an ionic compound, your I value, your Van Hoff factor, is always the number of ions present. And so with that, I hope that you've got enough to get the rest of this all finished up. All right. So with that, and I just realized that you didn't have enough view of the paper to see that last column. Sorry about that. Okay, I'm going to go ahead and stop recording here. You guys that are watching this on video, hopefully that helps you. And